Distributions. So, think back to the Milgram experiment we talked about when we were talking about binomial distributions. So, to refresh your memory, Stanley Milgram at Yale University conducted an experiment in which he tested how people react to authority. Participants were told they were assisting with another experiment in which they were supposed to administer electric shocks to a learner while the learner got wrong answers. The learner was an actor, and the buttons participants were told to push actually did nothing. The actor pretended the shocks were getting more painful, while a researcher in a lab coat encouraged participants to continue administering the shocks. 65% of the participants administered the highest level of shock. Each person in Milgram's experiment can be thought of as a trial. A person is a success if they refuse to administer a severe shock, and a failure if they administer such shock. Since only 35% of people refuse to administer a shock, the probability of success is 0.35. When an individual has only two possible outcomes, it is a Bernoulli random variable. Dr. Smith wants to repeat Milgram's experiments, but she only wants to sample people until she finds someone who will not inflict a severe shock. What is the probability that she stops after the first person? Well, the probability that the first person refuses is 0.35. What's the probability that she stops after the third person? In order to get to the third person, the first two have to administer the shock, right? 0.65 times 0.65, and the third person then has to refuse. So 0.65 squared times 0.35 is about 0.15. The 10th person, because she stops after someone administers the shock, or after someone refuses to administer the shock. So in order to get to the 10th person, the first 9 people have to administer the shock. And there's a 0.65 probability for each of those 9 people. So that's going to be 0.65 to the 9th. And then times the probability that the 10th person administers the shock. It's 0.0072. The geometric distribution describes the waiting time until a success for independent and identically distributed Bernoulli random variables. So we often abbreviate independent and identically distributed as IID. Independence, the outcomes of the trial don't affect each other. Identically distributed, the probability of success is the same for each trial. If P is the probability of success, 1 minus P is the probability of failure, N is the number of independent trials. Then the probability of success on the nth trial is 1 minus P to the N minus 1 times P. You have N minus 1 failures at probability 1 minus P, and then a success for the nth person. Can we calculate the probability of rolling 6 for the first time on the 6th roll of a die using the geometric distribution? All right, so a success is rolling a 6, and a failure is not rolling a 6. These are clearly defined. One or the other must happen for each trial. Can we use the geometric distribution? Yes, why not? Right? We can make this a Bernoulli random variable by saying that our outcomes are 6 or not 6. So the probability of not rolling a 6 on the first 5 times is 5 out of 6 to the 5th, times the probability of then rolling a 6 on the 6th time is 0.067, approximately. How do we find the expected value of a geometric distribution? How many people is Dr. Smith expected to test before finding the first one that refuses to administer the shock? The expected value, or mean, of a geometric distribution is 1 over P. So our probability was 0.35. 1 over 0.35 is 2.85, 86-ish. Now, is it possible to test 2.86 people? No, it is not, but the expected value is an average. If Dr. Smith performs this experiment many times, testing people until she gets someone that refuses to administer the shock, on average, it will take her 2.86 people. Our standard deviation for a geometric distribution is the square root of 1 minus p over p squared. So 0.65 over 0.35 squared, and take the square root of that. And I come up with 2.3 as the square root, as the standard deviation. All right, so she expects to test 2.86 people before finding the first one that refuses to administer the shock, give or take 2.3 people. All right, the standard deviation is the average deviation from the mean. All right. Because these are decimals, they only make sense in the context of repeating the experiment many times. If you only do the experiment once, you're only going to get some number that you have to test before it's got to be a whole number because you're doing a whole number of people. That's it. That's geometric distributions. So next week we are going to be doing some review, and then your test will be on Thursday.